Welcome to today's session. So our chair today is James Watt. So I'm going to hand over to you. We've got 19 in so far, but the numbers should kind of tick up a little bit soon.
First of all, I'll start off with good afternoon. Welcome, everybody. The introduction, intro and objectives. Karis can feel absolutely free to kick me because I've had not a lot of prep time for this because I've been a bit busy. But the general purpose of these meetings is to identify what research needs and to help distill what industry and stakeholders think are lacking, to highlight these to the or have an input into UKCCSRC and our members and our academics and researchers, just to make sure that we're not missing something that's emerging from projects and industry and the wider supply chain around CCS, but also to make sure we're relevant. And this is, I'm not going to rant, but there's a bugbear of mine is that some stuff that we see coming forward from research you can point to and say that's been done before. And part of this process has to be to highlight what's new, what's relevant, what are some of the issues that we face. We're joined by a number of people that are going to present. The format's simple. I get to have a little bit of time to talk about what's keeping me up at night as a transport and clusters guy. That's how I describe myself in CCS. I'm very much transport and clusters. We've got Andrew Wood from Harbour Energy, Eliane, I'm assuming that's correct, from Element Energy, Michelle from Air Products, Sam Bartlett from NPL, and Simon from HSE. And the format will run roughly 10 minutes for those speakers to get their list of what's keeping them awake at night out into the open. Then we will get to about 3:05, take a quick coffee break for 10 minutes, and then come back to a Jamboard activity to identify priority research areas. Being the age I am fascinated by the virtual whiteboards, but effectively it is a virtual whiteboard with virtual post-it notes that people can post questions, comments, points on, and it works quite well from an interactive point of view. That session will last for about 25 minutes. We'll do 10 minutes of clarifications for academics on the call, just to give us that space, and then a 10-minute wrap up of that at the end, and aim to finish at 4 o'clock. Please be interactive. Please use the chat for questions. I think we're currently recording. I don't think the Jamboard session after the break is recorded. Correct me if I'm wrong there, Karis, but
that's right.
Good. I was paying attention, see. So there's an opportunity to look back at these in the future. So yeah, we'll get started because I think some of the presentations might run over, and we'll just go through. So objectives. Next slide, please, Vicky. Is it? Yeah, there we go. So it's that key research needs. There's been others, policy storage, environmental impacts, and capture with transportation, and that covers pipeline and shipping. It needs to be pointed out, and that's almost a forgotten sector, I think sometimes. Slide 4, please. There was some previous transportation research identified in March 2021, and it's worth a recap. Something I'm a great fan of, whole system analysis. It's that connectivity of the whole chain and looking at the cross-train chain issues around transport, whether it's single emitters or clusters to stores, and how all those intricate loops may work, and feedback from the storage site particularly. I think is something that's a little bit underlooked at times. There was repurposing of pipeline infrastructures, looking at all the things that we look at in transport, like corrosion, equations of state, CO2 composition, leak detection, modelling of existing assets, and as well as for new, and flow metering, which brings us neatly to the last one, which effectively is the measurement needs identified by the Energy Transition Report from NPL, which I still think is a very good synopsis of some of the metering challenges that we need to face in in CCS and the transfer of carbon dioxide. Next page, please. Yep, that's the people that are going to be talking. We're talking from a industry policy and regulator point of view, and I think it's a relatively good mix. And just yeah, feel free to ask questions of these people while they're here. Next slide, please. So I'll go first. A little bit ahead of schedule. And I'm a bit, things keeping me awake at night on CCS. I mean, my main role is hydrogen now, but I do a lot of, still do some CCS work. But the things that concern me, the non-cluster problem, as I like to call it, how do networks and clusters enable remote emitters? It's a bit of a research area, I think, that's lacking. There's not a lot of talk about wider cluster plans. It tends to be left to the projects at the moment. And I think there's some particular economic issues with enabling emitters outside the clusters, and how what steps need to be taken within clusters to allow remote emitters to join sensibly later. I still think that there is an issue around shipping. I know Northern Lights is striding ahead with its designs and rollout, which is a massive shift from where we were just a few years ago. But there's still questions about the conditions, the logistics, the impact on pipeline flow of injecting shipping into particularly a networked or clustered system. So if you've got a pipeline going offshore already, taking from emitters, and you have a shipping solution that comes in, there's an intermittent flow pattern that has to be adapted, or a constant flow, and all the ullage and bunkering and buffering that may have to go into that system. So there's a little bit of a gap there, I think, that I'm not seeing a lot of work being done on at the moment. Network evolution. How do we achieve optimum transport for least cost? Particularly in the light of where the clusters are at the moment, that seems that this is something that's fallen adrift since the heyday of cluster studies in the early 2010s, when there were a lot coming out, and it doesn't seem to have moved on much since then. The integration of compression into capture plant in terms of heating, cooling, energy, and coming up with more efficient compression schemes than we've currently got, if that's possible, is something else that I wonder about. And the impact of composition. It comes up every time I go and talk to students. I do go up and talk in Edinburgh about CCS transport, but it's the impact of all the different emitter types, all the different changes in potential changes in flue gas composition within the range of the ISO spec for CCS transport on CO2 composition. Are we getting the equation of state models right, that they can cover all eventualities? What are the changes on mixing? You know, if we have two different emitters with slightly different compositions, what happens? How do we predict what happens if someone has an outage and something gets into the system that we don't like, and how do we design systems to accommodate that? And water content. There's still some questions there that as contaminants enter the system, do they impact the formation of free water? Do we need to keep the water content as low as it currently is generally on projects, because it does have a bit of a burden on the upstream systems. So those are my things that keep me awake, and those are things I think that are missing from the research body to a certain extent. My next slide is simply context. So this is the context of the problem we're talking about when I think about transport. On the left-hand side are UK emitters 2019. It's a simple Google map of all the EU ETS emitters, not all emitters in the UK, but EU ETS registered emitters. Back in the last time I updated it was 2019. You can see a lot of them offshore. You can see a lot onshore. The top right picture is from my same Google map, and it doesn't represent existing projects, although pretty close. You can see the East Coast joining into one store at Endurance. You've got Teesside to the north and Humber and Yorkshire to the bottom. This is kind of where we're coming from, where I'm coming from on clusters. In the how do we enable these clusters to consider out with what they would consider a cluster? Teesside is a tight cluster in that everyone's quite local, whereas the Humber is more dispersed but with bigger emitters. But how do we use those to enable the non-cluster emitters, the remote sites? What's the best thing to do? Because there is a significant cost penalty that's coming for some of these guys. If CO2 is their only option in the middle of the Pennines, you've got to transport it in somewhere. The bottom right is Teesside. These are the maps from the Teesside Collective back in 2015. And this is the level of integration problem you're talking about. There's 20, 30 emitters potentially on that network. And there's different options, and the colors represent different options. But how do we make that work? How do we ensure that that network operates properly? How do we make sure that everything maintains specification so that by the time it gets to the compressor station to go offshore, it's still compliant? How do we deal with outages? How do we deal with new emitters? What can we accept into the system? And there's not a lot of major thinking going on or research being done that I can see. You can see the occasional snippet of excellence that comes out, but it's just the pictures put it into context. We are talking about very wide networks of pipelines that have lots of different people feeding into them at lots of different speeds and rates and compositions, and how all of that is managed and addressed still needs to be, I think, thought about very carefully. That's it from me. I'm going to fall on the chairman's sword and finish 5 minutes early so that we can actually catch up with we've got 5 minutes spare for time management purposes. I think we'll take questions at the end. There's nothing appearing in the chat, so if people have anything absolutely pressing, just pop it into the chat and we can record it for later. Our next one is Ilian. Thank you.
No worries. Well, thanks a lot, James, for the earlier introduction, but also for introducing several of the points that I wanted to bring up today. I think I want to give a bit of a flavor to this presentation and really focus on the aspects of moving CCS from concept to real life leads to a range of research needs, which is what I'm going to be focusing on today. I imagine most of you here know about Element Energy. I won't spend much time on who we are, but we are a consultancy focused on low carbon energy and net zero. I'm a principal consultant within the CCUS and industrial decarbonization team and worked with several of you before. And really my focus has been on all aspects of the CCS value chain, from the capture to the storage and business models and so on and so forth. So I'll try to give a perspective of somebody that has been looking at the interaction between the different sides of the supply chain, of the value chain. But I also wanted to flag that recently, with the acquisition from the ERM group, we've started working a lot closer to projects that are developing into their kind of more implementational phase. So we are starting to also incorporate learnings from what does it mean to develop a commercial project and the real life issues associated with meeting regulatory requirements and more engineering real life issues. But in this last 12 months, I think the bulk of the work on relative to CO2 transport has been on the CO2 shipping angle. And this has been something that really we hadn't seen before nearly at all. but in these last 12 months, lots of people have been asking, what does that look like? And we've been doing work around understanding what the market could be like, what the options are and the costs and what infrastructure you need, onshore, offshore, and so on and so forth. And I will be taking this lens primarily today to discuss the research needs. So let's get on with that. There are 3 items which you can see on the left, and they are all linked. The first one relates to what does it mean to transport CO2 in, so to say, in real life, and then looking at multimodal transport, and finally some comments around the life cycle emissions with CCS. So let's start from the first one. And when we say real life here, we mean things that might be affecting the capture side of things, or even just the emitters, but also on the transport side. And I think the first point that I really want to bring up has to do with the variability in CO2 volumes, which could be linked to the fact that there is seasonal demands, like in the case for thermal power generation, that seasonality and that even intraday variation means that already in the last years, the load factors for combined cycle gas turbines have been in the 40% range on average, with large variation between different types of assets, depending on the markets in which they operate. And also in the context of heat, and therefore thinking about blue hydrogen, if it is serving the heat market and through grid injection, for instance, that's where seasonality and demand can also be expected. And this affects very clearly the possibilities for utilizing the assets of the transport infrastructure, whether it's ships or other assets. Fundamentally, that there is implications. And there is also longer term trends. For instance, if there is more renewables and better or cheaper renewables plus storage combination, what is the residual need for thermal power generation in the capacity market? For instance, what if there is green hydrogen at a lower cost? All of these kind of questions pose the overall question, which is what's the long-term utilization of the assets? That has cost implications, obviously. And I think I'd like to flag some of the main questions that come from this reasoning. The first one is certainly around the cost. What does that mean if you have to size for peak capacity, but then you don't utilize the assets fully? And how can you structure the commercial arrangements so that you can mitigate the impact of unplanned variations? And are these acceptable terms for one party or the other? And we have done some analysis. I just wanted to show why I believe this is really important. There is a representative case study on the right-hand side. And regardless of the exact details, we looked at how much does it cost to do CO2 shipping A to B for a certain amount of, certain yearly volume, assuming that you are operating 100% of the time. Well, in this case, for this example, we got 27 pounds per ton. And then progressively, as you reduce the load factor, you progressively increase by 10, 30. And then in the worst case, when you go down to 40% load factors, then that's nearly doubling. So that's clearly quite important cost implication. And if we think about it, what can we do about that? Of course, we can do something with the trying to be smart about the kind of combining sources of emissions so that you can maybe optimize that. But at the end of the day, peak demand is expected for winter for both power CCS and for blue hydrogen. That might change in the future, of course, that there can be other demand drivers that change this. And potentially also if there is shipping involved, well, winter seas could be rougher. That might mean slower shipping and therefore longer time and need for bigger for bigger fleets. So there are questions around that. But fundamentally also, at any time of the year, you could be operating a power plant at peak capacity and the whole value chain needs to be able to handle that CO2 flow. So there is a question of either you have a lot of spare capacity, which is sitting idle, or you need potentially a lot of buffer storage. And here it's an optimization exercise. There is room for mathematical modeling based on real life, hourly profiles of generation, if not daily or weekly, depending on what we're talking about. And there is also, of course, the question, at some point, it will be just too expensive to capture that last ton of emission. And then the question is it acceptable to not capture it? If there's a carbon price, that's probably going to be cheaper at some point. And here, there is a range of questions around that as well. So I think enough on this topic. And well, still sticking with real life, I think this is what James already talked about earlier. In practice, Andrew told us about the last mile of the transport and storage network. And in some cases, that would be it. If you're an emitter near the terminal from which then CO2 is sent up to the storage site, that's it. You don't need to worry so much more. Pretty simple, linear value chain from a large anchor project. But for other emitters, we expect that value chain will look quite different. And if we think about small remote emitters, you might have even trucks that do some sort of milk round between different small or smaller industrial sites that need to have local buffer storage. Then you might have a liquefaction phase before loading onto a ship, and then it gets to a port or the import terminal, and from there it's injected into the local pipeline network. All of this adds complexity and cost and may require much more developed markets than are in the horizon in the short term, and also business models. This depends on the geography, of course, and also on the characteristics of these sites. And at the end of the day, again, it's a matter of cost. What is the end-to-end cost of CCS, including also the increased cost of capture because of the lacking economies of scale, and then the complexity of the CO2 transport and storage network? We really need to understand what that will look like, because it affects the size of that addressable market for CCS as a technology class. And then at the end of the day, it's going to be a comparison with alternative decarbonization pathway, electrification or hydrogen, changes in products, anything really. And if there isn't business models, then something else needs to yield. So we definitely need to be very clear about what it takes, and then formulate suitable solutions to enable CCS where it is required, also in these sites. So I think from a point of view of system integration challenges, that was kind of it. I think I just would like to finish with considerations around the fact that CCS fits within products or processes that have kind of sometimes very complex life cycles. And I think we've been very aware in our field of the kind of progressive focus on topics that initially were quite niche, kind of nobody knew about them out there, or people not working on decarbonization on a daily basis, and then progressively hydrogen made it on the mass media, on the news, and then carbon capture. Recently, even CO2 shipping, we're reading about that, and scope 3 emissions and supply chains. That's been a very clear trend this last year. People are starting to ask the question: okay, you can decarbonize this asset, but where is the product used, or what feedstock are you using for these processes? Now, people understand that to get to net zero, you need to think about the whole thing. And there have been significant accusations of greenwashing that I think we all need to be wary of, and make sure that we have plans that justify us saying, no, that's not greenwashing, this is real decarbonization, and we have ways to tackle the entire life cycle emissions. And therefore, we also need to think about CCS, including the transport part, as compatible with net zero. So any project will need to be operating for at least 20 years. So they need to be alive in 2045, in 2050. They need to be compatible with the net zero economy in those years. So even if you address scope 1 and 2 emissions, and the rest of the emissions are not addressed, and they are the bulk of the CO2 that is released in that product life cycle, then there's going to be questions about the long-term viability of these models. And that has implications also for the transport, just to bring it back to the topic of today, because that's the infrastructure that requires some sort of certainty on the demand for this transport service. So there's going to be significant due diligence on the counterparties that are providing that CO2. And when we talk about supply chains to scope 3, that includes both the supply chains, as we're referring to the products that are decarbonized through CCS, but also for CCS itself, all the metals that go into the infrastructure, how the ships are fueled. Are they, with fossil fuel in the short term for sure, or are they also net zero compatible in the longer term? And all of that, again, leads to a number of questions. For instance, starting from what products will be used in 2045, and what the demand for these products will be like, and what's the role of CCS in reducing emissions in the context of the full life cycle assessment, and therefore, is it compatible with net zero? also quite including the downstream and upstream aspects. And finally, I think that's the question that we should help address is, what does it take to have CCS that is truly compatible with net zero and that can help decarbonize the entire supply chain? And of course, at the end of the day, what are the cost implications? So a lot of questions here, but I hope that this will stimulate some interesting research, and I'll be looking forward to reading the results from your research of this topic. So thanks a lot.
Thank you very much. We'll move swiftly on. Our next speaker is Michelle from Air Products.
So hi, yeah, my name is Michelle Rowe. I'm working at Air Products and been here with my sins for about 15 years now, coming up. I'm working in the CCUS, CCUS product manager, and I work in our blue hydrogen technology team. And so I've only got a few very brief slides, and actually a few of the topics we're going to raise, or I'm going to raise, have already been discussed. So it seems we're all kind of coming to the same conclusions. We'll get straight to it. So first, I just want to emphasize that the suggestions we're making in terms of research is really about it's new and industry-wide challenges that we're coming across, and it's mostly being driven by the fact where the scale of CCUS operations now is so much larger than anything historical in terms of CO2 applications, and that what we're trying to really encourage is to develop standards and to drive consistency in the industry, and to kind of try to gain global parity where we can. And then finally to research the topics in order to find best practices, enabling both safe and operable design. So it's not about trying to obtain competitive edge or anything like that. It's trying to make this consistent and safe for everybody across the industry. The first area of suggestions was in the pipeline aspect, and I think it was mentioned already by Andrew about the mechanical integrity of CO2 pipelines. So topics such as running ductile fracture and hoop stress design. So there are theoretical models, but some work is definitely required in improving the accuracy of these models to cover the entire range of sizes and applications of CO2 pipelines for CCUS projects. And in order to improve the accuracy of these models, it's likely field testing would be required to really make sure that the theories work in practice. And then by looking into these subjects, a request is to make recommendations as to what standards and design margins industry should be following in terms of material selection, material thickness, corrosion allowance, all the other aspects that are impacted by these behaviours of the material. It's specific to Europe. Again, I think it was mentioned earlier that the project in Humber is based on using supercritical pipeline, but our suggestion is to do a wider review of European CCUS applications to make not recommendations to review what the acceptability of these type of onshore pipelines are for permitting, what kind of objections will be raised for using supercritical onshore pipelines, because again, as already outlined by Andrew, that there are certain benefits to be able to transport in supercritical, but in some regions of Europe we're still being encouraged to use gas phase pipelines as instead of supercritical, and that as part of this is to do some process safety assessment for the range of pressures and temperatures and across a range of line sizes. So taking into consideration the different phases of transport. In terms of liquid transportation, we appreciate that there have been there's been a lot of work done in trying to review what the optimum pressure is for CO2 transport by ship. But our suggestion is to do a bit more of a full system evaluation of the reduction of the CO2 pressure from 15 to 7 bar. So although, as I say, that there has been lots of work done in this area, it's not, it doesn't fully reflect the whole impact of the liquefaction power as well. So yes, our suggestion is to look at this from an end-to-end basis and make an overall assessment as to what's the most optimum. There is a proposed consortium I've listed here that recently announced are going to be looking into this, called the CETO project, to develop low pressure CO2 ship transport. But again, it was just a suggestion to try and make sure that that is done in a way that it encompasses the whole end-to-end supply chain and makes and not just focus purely on the ship, the shipping aspect. The next point here was about material codes, and this is again focusing more on Europe, but it's the way that the codes are written and how it pertains to material selection for tanks. So there are differences in the regions and how the codes allow, how they guide you as to which materials you need to select for the range of operating conditions of CO2 tanks. And a suggestion is to kind of look into those codes and make an independent, impartial review to provide guidance on the material suitability for the complete design range of conditions the CO2 tank is expected to see. And quite clearly, the outcome of that research does have potential to influence the cost of a CO2 network by influencing the material selection that people and vendors take. And then just a general transportation in general subjects that could benefit from additional research is CO2 dispersion modeling after release. And I believe this has already been raised as a subject, but both for supercritical and subcritical conditions, how does CO2 behave? There are models, but their accuracy could certainly be improved. So that area could benefit from some more focus. And lastly, the impacts of impurities on CO2 transportation. So CO2 is quite unique in the way it behaves, and the impurities do change the way it behaves in terms of multi-phase flow and material compatibility. So defining some boundary limits acceptable for key impurities, and then outlining these impacts on material selection, corrosion allowance, operating, and the impacts of operating outside of these limits. So it's just providing some consistent standardized guidelines that can be available for across the industry, essentially. And then that's taking into consideration the different phases of flow that are possible. And I mean, we in our products, we have extensive experience in merchant CO2 operations, and so we do have we have a CO2 spec that we build and operate to, and we design new projects for. But it would be beneficial to try to get something that is industrial wide, and we'd certainly be willing to work with the research team on this topic. And that's all I had. So sorry, a bit shorter than previous presentations, but
thank you, Michelle. That's great. Sam Bartlett now from NPL.
So hi everybody, my name is Sam Bartlett and I work for the National Physical Laboratory, as has been mentioned a few times already. So I'm coming at this presentation from a slightly different angle to the other presenters, in that NPL are a research organisation, so we don't have research needs per se. We are the UK's National Metrology Institute, so we work in the field of measurement science. So I'm going to give you a presentation that kind of highlights a similar activity to what this workshop is aiming to achieve. But what we've done is looking at the measurement needs rather than the wider research needs. So my talk is on how measurements can support safe and efficient and cost-effective CCUS in the UK. So before we, as a government institution, before we can get to work tackling what we think are the high-level research needs or measurement needs required by industry, we first need to kind of understand what they actually are by engaging directly with end users, stakeholders, and industry directly. And that incorporates a lot of input from direct end users, industry involved, academia, also government and commercial stakeholders, so that we can build an understanding of what the gaps and in the gaps in the measurement science are, and where NPL's expertise can help bridge those gaps. So within our energy and environment sector here at NPL, we held a series of webinars in October 2022. So they would normally be undertaken in person, but obviously because of the pandemic, they were undertaken virtually. So they were attended by key stakeholders in the CCUS area, and we were able to take all of these findings to build a really clear picture of what we think the measurement needs are facing deployment of CCUS. So that information allowed us to develop this energy transition diagram, and I think was mentioned earlier by James. One of the key inputs or outputs from the last research needs workshop was our energy transition report, which in my previous slide there is a link to. So if the slides are circulated, you'll be able to access that. So this is the diagram that was built off that, and it highlights the key measurement needs throughout the entire value chain. So including, like, starting from capture, transport, storage, usage. Obviously, we're focusing on transport for today's workshop. You can see there's a huge array of different measurement challenges. Some have already been mentioned a couple of times. So things like CO2 composition and impurities present in the CO2 stream, equations of state, which is also linked to a lot of other aspects, including composition and the effect of impurities, and as well as other physical properties, and then things like leak detection, monitoring, and those kind of things. So with direct input requested directly from industry, we were able to kind of prioritize these measurement needs that then allow us to focus our research strategies in order to appropriately and ensure that the funding that we receive directly from government is being used to provide the most impact for industry. Unfortunately, for those of you on the call that know NPL or those that don't, we have a large number of different groups that specialize in different scientific areas. So we're kind of well suited to tackle these measurement challenges. With some of the groups, we can provide overlap to tackle challenges that perhaps aren't directly aligned with our research, but so we can be quite complementary in our approach. And these are just some examples, as you can see, that cover kind of the main areas or the main challenges from leak detection, flow metering, quality, materials testing, corrosion, etc. So within NPL, I work within the gas metrology group. So my expertise is kind of more focused around CO2 composition and purity and quality. So as I'm sure, as has been mentioned by a lot of people, that the impact of impurities in the CO2 can be quite far-reaching. So obviously we're focusing on transport for today. So the impacts of impurities on the integrity of the transport infrastructure is of key importance, but then also the effect on phase equilibrium, phase boundaries, and having multi-phase or two-phase flow it's important to understand that and how the composition and the impact of impurities can impact on that. But then obviously there is this slide is kind of coming at it from a whole systems approach. There's also impacts on kind of capture performance or information that you can deduce from with regards to how your capture technology is performing, and then storage integrity. So where we kind of look to gauge is, in order to perform measurements of the various myriad of impurities that are expected to be present in CO2 streams and CCS, the fundamentals of performing a traceable and robust measurement require primary standards and primary methods. So that's kind of where we come in order to develop those primary standards and primary methods that require reference materials and standards, in order to then build upon that, and that these kind of primary methods can then be applied by industry, so that measurements can be interpretable, and kind of there's overlap and a quality layer within the measurements. We also are doing a lot of work on how we can develop and optimize equations of state. So luckily we have a whole heap of different groups that can provide robust data, or we can help develop and understand various physical properties. So in my group, we're looking at gas composition, but then we have other groups that are well placed to be able to provide kind of input into the other physical properties that are key to building these equations of state. This one's not so important for the transport workshop, but I just thought I'd highlight it anyway, in that some work we're doing is around capture materials testing, with a specific focus on measuring the downstream gas stream from the capture technology, as obviously that's becoming a more important aspect of people or organizations buying capture technologies, obviously installing them on their plant, and think they need to obviously understand what the downstream gas composition looks like, and whether further cleanup may or may not be needed in order to meet specifications that are being set by clusters that have been mentioned, or just need to meet any kind of specification. So we're developing a system based on a microreactor, where we can expose the different solvent or sorbent materials to varying gas compositions depending on the flue gas that is expected to be used with, and we can kind of do this on a small scale rather than a large scale. It's like a desktop based microreactor, and then we can expose that to kind of a ramped cycle, kind of mimicking extended periods of use, and then attach the output of this system to our various suite of gas analyzers, and kind of give a kind of a detailed diagnostic of what the gas composition looks like, and whether there are any trace level impurities that are kind of critical, and also give you kind of the sorbent or solvent producer some information as to any degradation products. And then I just wanted to highlight this project that will be kicking off in the summer this year. So it's coordinated by NPL, and it's the first collaborative European project looking at metrology specifically for CCUS. So there's a list of some of the partners involved in the work, and we'll be looking at tackling the 4 of the main challenges or measurement challenges associated with CCUS. So flow metering, emissions monitoring and leak detection, chemical metrology, so that's to do with the composition and in the effect of impurities, and then physical properties, so looking to further again develop those equations of state. That's all for me.
Cool. Thanks, Sam.
Thank you.
And our last guest is Simon Grant from the HSE.
Thanks very much. I'm sorry, some people are probably sick of hearing from me because I've given a little talk like this at the end of the other sessions on this UKCCSRC meeting, so apologies for that. So the aim of me coming along to meetings like this is to try and re-engage with the CCUS research community. So James mentioned that sort of there's been a bit of a quiet period for a while on CCUS, and we had the same thing in HSC as well from 2017 onwards, after the government cancelled the last competition. And we've been busy on hydrogen and ammonia and things more recently. So we're trying to get up to speed again on CCS. I gave a talk on Tuesday about knowledge gaps that we understood existed, that covered some of these transport related issues. We've been out of things for a while now, so part of the aim of that talk was to sort of see whether any of those issues have been, the knowledge gaps have been filled since then. And it's interesting to hear that some of those things that the previous speakers have talked about running ductile crack propagation and dispersion modelling, those are still, research is needed there. So that sort of chimes with what we were talking about too. So yeah, if there's research that has been underway in the last 5 years or so that you've been involved in, that you think we should know about, please do get in touch with us about that. Also, if there's new research projects that are proposed as an outcome perhaps of this meeting or other things that you've been discussing about. I mean, in the past, we were engaged in the Cool Trans research project, where I went along to sort of steering committee meetings just to see what research was being undertaken there. And I think that was a really constructive and productive sort of relationship that we had with National Grid and the other partners that were involved in that project. So if you think it would be useful for HSC to have some oversight of the research that you're doing, to avoid any kind of surprises at the end, then please get in touch with us about things like that. I'm a scientist, so I work at the research division in Buxton. There's other regulatory colleagues that are better placed than me to talk about the regulation and policy aspects, and there's a presentation by Trevor Sexty that, if you're interested, I can share that with you if you get in touch with me, or Catherine, I think, is on the line as well here. So yeah, that's it for me. Yeah, and to end with, I guess this is the last meeting. So thanks very much to UKCCSRC for arranging these meetings, and for Karis and everyone on the team there. I think you've done a great job. So yeah, thank you. And yeah, thanks, James.
Thank you very much for that, Simon, and your kind words for the team. They do put a huge effort in the background, particularly controlling the chairman. So on the schedule, we're running a few minutes late, but I didn't want to cut anyone off. We're scheduled for a coffee break for the next 10 minutes, or at least until 15:15. So I'm just gonna, we'll reconvene at in 10 minutes, because I know it takes me roughly 10 minutes to get downstairs and make a new cup of coffee and get back upstairs. And then we'll start with the Jam board activity at 15:17 or thereabouts. There's no need to log off. You can stay online and mute, or if you want to, you can hop off and hop back on again. It's entirely your choice. So I'll stop talking and we'll see you again in 10 minutes. Thank you.